Okay, welcome everyone. Let's wait for a few seconds until everybody joins. Okay, so while we are waiting for more people join, I just want to make sure you guys can hear us fine.
I'm hearing good. I mean, this is
Okay.
also a check.
Okay, just want to check that the audience can hear us talking fine. The volume. Okay, sounds good. Yeah, thanks for the response. Okay, maybe I think let's get started. Okay, so good afternoon, everyone, or good morning, everyone, depending on where you are. So welcome to this new episode of this Health Application Society online seminar series today. I'm Qiu Chen. Okay, today it's our great pleasure and honor to have Dr. Andrew Lee speaking at our seminar series about their award-winning research work. Dr. Andrew Lee is an assistant professor of operations research and the BP Junior Faculty Chair at the CMU Tepper School of Business. He completed his PhD in Operations Research Center at MIT. His research interests are in statistics, optimization, and machine learning, with applications to operations management and medicine. Their paper, Optimization in Race to Liquid Biopsy, which he will be sharing shortly, has won the Inform's Peer Scholar Best Paper Award last year, which is one of the most prestigious awards in the fields of healthcare and management science. So for our audience, welcome to leave your questions and comments in the chat box. We can let Andrew to decide whether he will gonna take the questions on the fly or discuss them in the end. So without further ado, please join me and welcome Andrew to share his work. And Andrew, the floor is yours.
Thanks, Qiu. That is a great introduction. And let me, while we're starting this talk, let me just say like a reverse thank you. I mean, thanks to you guys for putting on this series. I think it's I told you guys privately, but like I think this is COVID has kind of a bunch of negative effects, but I view this as one of the positive ones, right? That we kind of organize seminars like this, and if anything, information gets disseminated faster. Yeah, so what I'll eventually talk about some some pure Scala stuff. But what I've liked about this series so far is that the topics have been pretty broad, right? And we're kind of, I mean, like I'm talking to a community of people that work in OR, right? Optimization, stochastic modeling, and I want to connect that to kind of problems that I have found in healthcare, specifically in medicine. And so what I'm going to try to do is the following. I'm going to set up this talk in kind of two parts. You're going to see right now that in this title slide, I have only my name here, and really my name shouldn't even be there. So this is part one of the talk. Andrew Lee is named there as the speaker, but nothing that I'm about to say has anything to do with me, right? View it as kind of a lecture, right? I'm not, this is kind of work thanks to a bunch of biologists and bioengineers and biochemists, right? This has nothing to do with my name is not stamped on any of this. In part two, I'll try to connect all of that to kind of what I think people in OR can add to all of that. Okay, and there I'll introduce my co-authors and maybe myself too. But I want that divide to be clear. Okay, so for at least I see 1:05 p.m. on my own clock. for at least the next 25 minutes. Okay, nothing about what I'm going to say has to do with me. Okay, and I say that very carefully because I'm going to use the royal we kind of very loosely. So I'm going to use the word we all the time, and I need you to understand that we did not involve me. Okay. Finally, let me echo again. If you have a question at any point, I encourage you to put it on the chat. Zoom is a very complicated object. And what I've decided for this talk is that I see your chat, or I see the global chat. If you post a question, I will see it. I have it on my screen. I'll try to answer it very quickly. Okay. So let me tell you about what's going on kind of in the race to a liquid biopsy, right? What is even a liquid biopsy? I'm talking about blood testing for cancer specifically. Okay. So let me just say kind of statements that you would grab from kind of the popular news today, right? So number one, cancer treatment, which we would probably call, medical question, the golden medical question right now, cancer treatment is heavily dependent on the stage at which that cancer is diagnosed. Okay, so even the current numbers are something like, let's take lung cancer. If you're diagnosed with kind of like a late stage lung cancer, you have sadly an under 10% chance of 5-year survival. If you're somehow luckily enough to be diagnosed stage 1, that's very early, you actually have over 90% 5-year survival. Okay, so this is a very first order kind of question, right? It's just detecting that cancer. Unfortunately, even right now, detecting early stage cancer is an open problem. Right? And that's because we only have 2 ways of doing that. We have a very accurate way of detecting early stage cancer, and that's the biopsy. That involves, the word biopsy means let's dig out tissue, a sizable amount of tissue from your body, and look at it under the microscope. That obviously works very well in terms of accuracy. But I put the word invasive there on purpose. It's invasive. Like, there's a reason that you don't go to your kind of like yearly checkup and get biopsies done. That's not a fun procedure. Okay. On the flip side, there are procedures that are kind of equally uninvasive, but frankly equally inaccurate. Right? We can kind of rely on measurements that don't, frankly, don't suck as much, but their accuracy itself. And that's why for a long time, there's been this open problem of figuring out what's called a liquid biopsy, right? It doesn't necessarily have to be blood, but for today, let's just take it to be blood. A simple blood test to detect cancer. Right? And the idea would be, this would just be done in kind of your yearly blood work, right? Among the other things that your yearly blood test is detecting, diabetes and so on, it would try to detect early stage cancer, right? I claim this would be as good as curing cancer. Okay. What I'm going to talk about today is one of 2 different approaches towards this goal, right? Towards this kind of gold standard. Okay. The approach I'm going to talk about today is the genomic, the DNA approach to this. So let me talk about kind of this is we'll call this kind of Bio 101 by a person that only took Bio 101. This is biology from a non-biologist. Okay, and I promise I'm aware of my own misunderstandings too. Okay, so call me out on anything that you hear. Okay, here's kind of why you should believe that something about DNA should work here. Okay, now in some sense, DNA is the perfect signal. Right? What this is in 2022, this sentence is obvious, but this was not always obvious. Okay, cancer is caused by DNA mutations. Okay, so we'll say this would like if this talk were in the year 1990, that would not be fact, right? That would be up for debate. But in 2022, that's not up for debate. If unfortunately you have a tumor that was caused by a set of DNA mutations. And what that means is if somewhere in your body you currently have a tumor, that is because a set of mutations occurred in your DNA. So that's happening there. Fine. Where is the signal, right? Why should your blood be able to find that. Now, here's the idea. This is also an idea basically from 1990, say 1980 to 1990. Okay. Whether your cells are healthy or tumorous, whatever, okay, there is a notion of cell-free DNA. Okay, inside your body, there are healthy cells all the time, inside every single cell, right? From Bio 101, there are strands of DNA. Now, your cells die every once in a while. Everything in that cell gets discarded. Occasionally, DNA gets preserved, right? You have to view the cell as kind of a balloon that's holding this tiny little DNA particle, okay? Occasionally, those get let out. That's what's called cell-free DNA. Where does it get let out to? It gets let out to your bloodstream. Well, this is perfect now, right? Because the idea is this. Somewhere in my body, I have a tumor. I don't even know that the tumor exists, right? But every once in a while, some of those tumor cells die and they release strands of DNA. That DNA was what caused the tumor to begin with. Right? So I should be able to, technically, that's where the signal is. I should be able to go back into that blood. That blood is now flowing, by the way, anywhere in my body. Right? So I should be able to draw blood from anywhere in my body, sequence that DNA and say, wait a second, this is the DNA that would have caused a lung tumor to begin with. That means Andrew has lung cancer. That's the basic idea. I put some numbers here. I put one number that there's going to be concrete numbers. There's going to be many concrete numbers throughout today, right? But I'll keep drawing back to them. None of them are fake. One concrete number is this, okay? The generally accepted number is this. If I have a lung tumor or any sort of tumor, right, and that tumor starts releasing DNA into my blood, that blood, obviously, that DNA gets mixed with healthy DNA. That's the problem, right? The concentration, the best concentration I can hope for is 1 in 10,000. Right? Meaning that in my blood at any moment, there's kind of like a ton of this cell-free DNA floating around. That's kind of the opportunity, right? But it's not all cancerous if I have cancer, right? Most of it is still healthy because most of my body is still not like a tumor, right? The best concentration we can hope for is 1 in 10,000. Okay, just keep that number in mind because I'm going to come back to that. But at a higher level, understand that there's nothing biologically, there's nothing wrong here. Cell-free DNA was only discovered in 1990 before we could even sequence DNA. But the basic idea that you could use that to detect what cancer somebody has, that's a very old idea. Okay, by now we're talking a 30-year-old idea. Just hold on to that. There's nothing no biologist could say that this plan for finding cancer is kind of like on weak footing. Okay, this is very much on strong footing. Okay, so this is 1990. In fact, let's zoom forward now. Right now, we're sitting at kind of the beginning of the 2020s. I'll tell you why it took 30 years to get here, but we have kind of prototypes of this, okay? And as of, let's say we're in April 2022, let's say as of March 2022, there have been from academic labs 2 very promising prototypes of this idea. Okay, one from that I'm going to call Cohen et al. That was a science paper from 2018, and then Liu et al. That's 2020. Just for today, I'm going to focus on that Cohen et al. Paper. Okay, this one is one that you might have even seen, even if you, everybody I imagine in this audience, is kind of reading medical news. But I mean, you might have your friend in finance might have sent you this article, right? In 2018, this was big news. There were huge claims about a new $500 blood test to detect cancer before symptoms develop, right? This was very exciting stuff. Keep this name in mind, Cohen et al. I'm going to tell you again, we're still in this is talk first half, right? Everything is nothing about me, right? I'm going to, in fact, by the end of this first half, explain to you what Cohen et al. Did in every sense, right? In terms of data and so on. So just keep that name in mind, okay? But in any case, we're getting close. right? This was huge news. This Forbes headline is a bit of an exaggeration, but not that far off, okay? We're getting close, right? To the point where there's also startups doing this right now, right? I have 3 right here. There's probably 10 by now. But let's stare at the bottom left in particular, Grail. Grail is really close, right? In fact, if you talk to somebody at Grail right now, they would say they're like a month away. Let me tell you where Grail is right now in this game of developing kind of a blood test for cancer based on this biological idea. Okay, let me tell you where they're at and why that's kind of, I mean, they're close, but I mean, the finish line is still far. I mean, if they were done, then the last time you saw a doctor, you would have had this test done, I assume. Okay. Here's where we're at right now in 2022. Grail has a test called the Galleri. Okay. I'm going to walk you through just what you would grab perusing their website. Okay. There's zero kind of inside information going on right now, right? Absolutely, this is what you would grab. So the first thing you grab, if you stare kind of at the fine print at the bottom, is that you would see this test is something you can take right now for $949. You can have this done. You can leave this talk, right? Go see your doctor. This is a $950 test. For most of us, our insurance will not cover this, right? But I mean, if you have that many dollars kind of floating free, please go run this. That test claims to do the following. Number 1, it will detect at least 50 different cancer types. Okay, but what does that mean? What does it mean to detect cancer types? Let's now I want really the fine print for a second, okay? The claim is, and I shouldn't say that skeptically, this is achieved, okay? What this test achieves is a specificity of 99.5%. I'm going slow here. I want us to understand. Specificity means if you do not have cancer, what is the likelihood the test correctly tells you you do not have cancer? This is very important because speaking to any audience, I don't care who it is, the fact is most of us currently do not have cancer. It would be very devastating to be told that we do have cancer incorrectly. So this specificity, right? Again, the fraction of the percentage of time that you tell somebody that who does not have cancer correctly that they don't have cancer, that's frankly the most important number. Okay. And this is not the Galleri folks didn't invent this, right? Like 99% specificity is not gold standard, is baseline for any kind of test, including maybe the COVID tests that you've taken recently. Okay. We have a very clear sense of what it means to incorrectly tell somebody that they do have a disease. Okay. So this is baseline. I would like to not tell a bunch of healthy folks that they do have cancer. Okay, but the problem is there's an easy way to do that. I could just tell everybody that they're healthy, right? So the flip side of that is I want sensitivity, right? For the people that do have cancer, I would like to catch those folks. I would like to correctly, if somebody really does have lung cancer, I would like to tell them, you know, hey, you have lung cancer. It's bad news, but I mean, that's the whole point of this test, right? For that, the sensitivity claim, and I shouldn't say claim, this is achieved, 77%. Okay. And again, I'm going to come back to these numbers. So let me at least repeat the order one more time. This is a under $1,000 test that detects, you know, about 50 cancer types. Specificity needs to be near 100%, meaning healthy people, we need to get that right like all the time. Sensitivity, we'll look for about 75. Okay, these were numbers I grabbed from Galleri's web page. And this matches, by the way, kind of like general understanding of cancer tests. How do they do this? Now is where this is still not now like I'm probably going to use the word we even more now. It still doesn't involve me. We is kind of is Cohen et al. This is still a description of generally how this is done. Okay. So here's the basic idea. Here's how you would develop such a test today if you were kind of hired by Grail. Okay. First, let's just talk about data. Right. I mean, biology is complicated, but the biologists, just like us, make simplifications, right? So if I look at a strand of DNA that is 3 billion addresses, I'm going to grab onto that word address because I'm going to say the word address like 100 more times today. Your DNA is just a long string of 3 billion addresses. Right. And if you remember Bio 101, at each address, there is a letter, A, C, G, or T, that has a very real physical meaning, whatever. I only care about mutations, right? Or we, the royal we, only care about mutations. The idea being this: we, royal we, have in mind a reference sequence. What this means is healthy DNA. We have a notion of what healthy DNA looks like. And so when we actually sequence somebody else's DNA, all we do is we say, hey, there's a moment here at this address, right? 2 billion in, at this address, the letter that you have there doesn't look like the rest of the world. Right? And we're going to call that a mutation. I'm obviously hiding a bunch of stuff, right? And in fact, I wouldn't be the person to talk to, right? I mean, this is the work for, really the bioinformaticians, right? Ultimately, what the bioinformaticians can give us is this: zeros and ones, right? It's still 3 billion long, right? But it's in their opinion, hey, at this particular address, kind of, we saw something that didn't make any sense. Or at this particular address, we saw something that was a bit off, right? This is a very important process, by the way. I don't want to discount this, right? There's a ton of work that goes into this. I mean, the reason that I have black hair and somebody else has brown hair is also because of DNA, right? So the bioinformaticians distinguish what distinguishes, brown hair, black hair versus tumor, not tumor. So this, I'm going to take, I trust those folks. Right? This is a very, very large and intelligent community. This is raw data for me, the zeros and ones. Okay, so somewhere there's a black box that does that. Now, okay, now we can have some fun, right? Because now what has been done in kind of the best data sharing community that I've ever seen is we, again, royal we, have sequenced the DNA inside a ton of tumors. Okay, and so we publicly are sitting on data that looks like the following. Okay, every row you can imagine is a different set of data, is a different person, right, whose tumor we've actually sequenced. The columns, right, I'm very much drastically underdrawing the width of this table here. This table is really 3 billion wide, right? Because I am literally talking about every single DNA address. If you look inside the table, you're going to see zeros and ones, right? And when you see a 1, that just means, hey, there was a mutation there at that address for that person. If you look at the far right of what I just drew here, you're going to see labels like liver, stomach, pancreas, breast. Those are the different tumor types. Okay, this is the data that we, and also Grail, are sitting on right now. Okay. What we could do right now is just talk about machine learning for the rest of today, right? This is not I want to convince you, we're not talking about a machine learning question right here, right? This is actually a ton of data that, truly we have, this is not made up. You can download this data right now, okay? What I want to convince you of is that we actually are sitting on a really interesting optimization problem, okay? So here's the basic idea. At any point in a kind of a DNA talk or anything involving DNA, you'll see a picture like this, right? Which is the cost of sequencing DNA over time, right? The vertical axis is cost, the horizontal axis is time. Don't let me convince you that this is a useless picture. This is awesome. The vertical axis is on log scale. This is amazing. Something happens though that I want to point out kind of in 2007 to 2008. So about a third of the way through horizontally. you'll see kind of this green line is decreasing linearly and then kind of drastically starts dropping, right? That is because of what we call next generation sequencing. This talk is not about next generation sequencing. I didn't invent next generation sequencing. That is a technological advancement that happened around that time. The net result, right, is what gave us all of the data that I just talked about in the previous slide, right? Right now, in 2022, it only costs about $500 to sequence your entire genome, right? If you were to, this sounds weird, but if you were to grab one strand of DNA from your body and give it to one of the many companies that'll do this, $500, they'll do this. Okay. I am only citing these numbers because ultimately this is going to come down to cost. Okay. In fact, let's just do some calculations for a second. Right? And you can push on any of these numbers at any point if you want, right? But here's the kind of the basic math. So if we're going to run a test, the actual variable cost needs to be about $100. Now, I already showed you that the Galleri test costs $950, but that's I mean, that accounts for the marketing. The variable sequence cost is about $100, and this is a very well understood number. Okay. If you want to sequence a single address of your DNA, I'm talking about one letter, just once, right? Based on the data that I just gave you, that would right now cost 10 to the minus $6. That's $0.000001. Whatever, but we don't do that. What we care about is sequencing each address 10,000 times. I put the word 10,000 here in red on purpose. 10,000 is because the concentration of the tumorous DNA in your blood. Don't forget the biological game here, right? You either have a tumor or you do not. If you have a tumor, all we are hoping for is that that tumor is releasing DNA into your bloodstream. Even if that DNA is released into your bloodstream, the concentration is still only 1 in 10,000. Right? So if I want to sequence a certain address and detect and use that as a signal for one particular cancer type, I would technically need to sequence that 10,000 times. The net, if you just work out the math, I'm okay if you just grab onto this final number. Out of the 3 billion different addresses in your DNA, we can only really look at about 10,000. Okay, and that 10,000 number, I'm going to keep coming back to a bunch. Okay. I'm not sure it's exactly 10,000, but I promise you I'm not off by a factor of 2. So let me explain the game one more time. And now this picture actually will be drawn, well, it's still cartoonish, but it's reasonably to scale, right? The basic idea is this. You're not going to be able to look at all of this data, or you're not going to be able to do so if you're trying to sell a test that you can bring to market. Okay, your game, if you're trying to play this, to design a test that can actually be brought to market, is the following. You're just going to select a few addresses. The columns in this table are addresses. So maybe you start with this one. Right? Hypothetically, if you had sequenced this address, you would have detected in this picture 3 of the different cancer patients. Now you don't have to sequence just one address. Maybe you add 2 more to your panel. Right, and here you actually would have gotten about 33%. Okay. You imagine a bigger table. Obviously, this is cartoon. You imagine a bigger table that has, 25,000 rows and 3 billion columns. That's actually the game you're playing. And that brings us to Cohen et al., Science paper, 2018. I want to say this picture, I literally just took a picture and, snapshotted it, copy and pasted. I did kind of a little more and less. We have reproduced what they've done here. Okay, this is a reproduction of what they've done, meaning we grabbed the exact same data, used what we believe to be exactly their algorithm, This is a near reproduction of what they have. What's going on here? On the horizontal axis, right? You can imagine giving yourself different budgets in the game that I just described. This is, by the way, I mean, this is not a, let me go back. This game is a very well-defined game because this data set is one that you can download right now, right? This is in some ways like a Kaggle competition, okay? This data is not hypothetical. You can download this data right now. It's in a database called Cosmic, and you can challenge yourself to the following game, right? For whatever number of a budget, let's say, of columns or addresses that you want to look at, you want to detect the number of rows, that is tumors, right, that you would have identified. Okay, so it's just sanity check looking at this picture. Obviously, this proportion detected, this curve is increasing. The more addresses that I sequence, the more tumors I am going to find, right? By the way, that proportion detected, you can view that as sensitivity if you want, that word sensitivity, right? Okay, I mean, it passes sort of basic sanity checks. Let's look at absolute numbers here. I said 10,000 addresses is kind of a good baseline in terms of cost, okay? Meaning what I've just shaded here in red, that's really where we're living in terms of what we can do, in terms of what we can afford. Okay. Now that Galleri test that I just talked about achieved 75% sensitivity. Now I'm talking about this red box. All I want you to take away from this picture is that the black curve does not intersect with the red area. The red area is what we might call the bring to market area. In fact, let's call it that, the bring to market area. The black curve is what is achieved right now, circa 2018. You can, by the way, break this down. I have this table. You notice at the top, I've called it all cancers. This was technically done over 8 different cancer types. This is still a reproduction, complete reproduction of what was done in that 2018 science paper. Okay, you can kind of see that certain cancers are more easily detected than others. Okay, that's fine. I'm about to enter part 2, where I tell you kind of what me and my co-authors did. I'm going to enter, just for the next 2 to 3 slides, a hybrid zone. Okay, where I'm going to, in fact, just say this is what the community would have done, right? Folks that kind of think about optimization, because in fact, I hope kind of where you're sitting right now, you've already thought, what this is an optimization problem. Let's go back to the data. Okay. This is a problem called not set cover, which this is max cover, right? Which is just kind of the flip objective versus constraint of set cover. Think of it as set cover if you want. This is vanilla set cover, that table of zeros and ones that were given, by the way, right? There's no work here. This is given to us. Okay, that is a set membership matrix if you want. All right, or put it another way. Okay, I mean, you think of max cover broadly. What is max cover? Max cover is I have a bunch of elements in some space. I have a bunch of subsets, right? And I want to choose, I have a budget of subsets, and I want to grab as many elements as possible. That's it. That is this problem. The rows of this table are the elements, right? Those are, I mean, it's more deep than that, right? The elements are, frankly, I mean, tumors, right? The columns are different subsets, meaning the DNA addresses and what they actually would detect. Okay, but otherwise, this is no different. I could take out the labels and pass this on to somebody across the street. I see across the street a large CS department. They'll do this for me, right? We do this ourselves, in fact. This problem is massive. I mean, this is a huge max cover problem, and we could talk a long time about the math of this and kind of approximation algorithms and blah, blah, blah. I don't care. I have this data set, right? And what we did is, I mean, like we applied a few hacks, but we solved this. I mean, solved, not approximated. This is solved, right? Which is fine because it's not about theorems yet, right? I just want to solve this problem. So going back, this is what you would have seen in that science paper, 2018. Okay. And here's the result of the kind of optimal solutions now. Okay. Let me show that one more time. The animation I know is that we're subject to some sort of lag and data, whatever. So this, what you're seeing right now, I'll keep talking. What you're seeing right now is like 9 different colored curves. This, I mean, it's reproduced from that paper, but I promise it's a faithful reproduction. Okay. What I'm about to animate now, all of the gray curves are the old curves. The red curves are the absolute optimum. Okay, and I don't even care so much about the lower side. Like these are upper bounds on what you can achieve. And by the way, I mean, we can talk separately about why the original paper did not just go about solving this max cover problem. That's irrelevant. I actually hope your takeaway as of where we're standing right now is kind of like a huge dud. I really hope right now, I shouldn't say I hope, my reaction when I saw this was optimization provides no value. Not no value, but I mean really second order. Go to the top left for a second. Let me zoom in back to the top left picture. Here's where we're at, right? I wanted to, using 10,000 addresses, achieve a sensitivity of 75%. That's the pink area in the top left. I haven't gotten there, right? If anything, I'm really impressed. I don't think the original folks that did this used optimization software, but considering the fact that the red line is the absolute optimum, they did pretty well, okay? And so here's where I'm going to kind of end part 1. I mean, I've already kind of talked about stuff that my co-authors did, so it's getting a little hazy here. But this is kind of where I think, right, like let's back out for a second, right? At this point, data is not going to save you, right? Data is not the bottleneck here. We don't need more data to build this test. We could use technology. Technology always reduces cost. Right, but if you kind of, I'm not going to go back. If you kind of go back to that picture like 20 slides ago of the cost of DNA sequencing, you'll kind of notice that flattened out. So, okay, I mean we can kind of wait for DNA sequencing to just reduce in cost, right? I claim there's a third step. Right, and that's kind of where we, and now we, I mean we, me, my co-authors, and us, kind of the collective OR community. This is where I think we can actually step in. Okay, so let me tell you let me end today with telling you kind of what now we, me, and when I say we now, I will mean we, me, and these co-authors here. 2 of my students, Kirigan and Suja at CMU, and then also another faculty member, Sridhar Tyre. What did we do? I think what we did was kind of take one step towards an algorithmic solution to this. Okay, again, the solution is not going to come from collecting more data, though we always are. The data is trickling in slowly. The data, a solution could come from technology, but that feels at this point to be just trickling in slowly, right? What can kind of we now, the optimizers do, right? Here's where I think the kind of fun begins, right? So I call this adaptive panels via greedy algorithms. Let's just let's use the word adaptive for a second and just stare at that, right? The basic idea is this, and I suspect you were thinking this already. Right? It was kind of our first idea, right? We don't have to, the tests we were just talking about were completely non-adaptive in the sense that they kind of came up with a certain panel, a set of DNA addresses to inspect. And that was applied to every single person. Now, the fact is, some folks are kind of easier to, I don't know, evaluate than others, right? So the opposite extreme of this is a fully adaptive test, right? One where, look, we grab somebody's blood, we look at a certain address, we sequence that and look for a mutation. Whether or not we find a mutation, that dictates the next address that we look at, right? More generally, I'm just saying, let's perform this test in stages, right? And in particular, the addresses, the DNA addresses that we'll look at should depend on what we saw in the previous stages. That's it, right? That's the same way we use the word adaptive in kind of what we do, right? This is very much feasible, by the way, right? You could say like, well, that's a mathematical construct. It's not. Right, the company that does this is kind of averaging costs across individuals. Right, it's okay if every once in a while there is an individual that takes $1,000 to identify, if the other 90% of individuals get reduced down to $10. Right, so if you're just doing the business of this, the math of this, the accounting of this, right, that $100 cost constraint only needs to hold an expectation. Right? So this is very much rooted in, if anything, the business of this. Right? Or put another way, the hope is that for a $950 Galleri test, or the whatever $100 cost we've kind of imposed on ourselves, the hope is that we would get higher accuracy for free. Right? Hopefully substantially higher accuracy. Right? So that opportunity is just sitting there. I mean, that's kind of what we were thinking. Now there are challenges. There's challenge number one, which is that this problem is hard theoretically. But frankly, the previous problem that I showed you, the max cover, that was also a hard problem theoretically. Max cover is NP hard. Still solved it. I mean, concretely solved it via Garobi. Here, I mean, like really hard. Hard and hard. I mean, like NP hard and kind of like you're not going to solve it, you know, with Garobi. Okay. So that's kind of where we're sitting. I mean, my co-authors would be mad that I won't be able to cover every single thing that we did. Let me tell you kind of one thing that we did, and I'll kind of refer you to the rest of our paper if you're more interested. Okay. Now, from where we're sitting right now, I do need a model. We're in the second half of this talk, meaning at this point, I do get to insert modeling kind of assumptions, but also you get to now call me out on anything, right? In the first half, if you had kind of challenged me on any sort of modeling assumption, you actually would have been challenging some sort of large biological community. At this point, it's really like me and my team modeling. You should feel very comfortable saying, no, I don't believe the following assumption. And that's kind of where the future directions might go. Okay, so at this point, I cannot say that doctors back up kind of the major assumptions that are about to make, but I'll tell you when those assumptions are made. Okay, first, I need a model for DNA mutations. Okay, this is just notation. I want to detect different cancer types. Remember, the Galleri test detected like 50 different cancer types. Okay, so I'll use capital T to represent the number of cancer types that I'm trying to detect, and I'll just number them 1 through capital T. And I'll do you one better. I'll use the letter little t anytime I'm talking about this. Okay. DNA addresses, the 3 billion of them, I'm going to call them 1 through capital A, and I'll use little a to index those. I'm going to assume the following is given. This is actually not the crazy part yet. I'm going to assume the following is given. It's a big old table, a big old matrix. It has capital T rows, 1 for each cancer type. So this is different. It's not a single person now, 1 for each cancer type. It has a column for every single DNA address. So it's still 3 billion wide. And that matrix, I'm going to call capital P. Here's where I'm making an assumption. And here's where you can and should push. And in fact, I'll kind of tell you where you might go. Okay. The basic idea is this. If you choose to sequence a certain address, what you're going to see is a coin flip, a Bernoulli random variable, right, whose mean or whose probability of heads is equal to PTA, the entry of that matrix. What is this matrix actually storing? This matrix is actually storing, let's say, the mutation probability for every single cancer type at every single address. Okay. Actually, frankly, even there, I haven't made an assumption yet. The key assumption now, and I'll just say it in words, is independence. Right? So one of those rows corresponds to, let's say, lung cancer. And the idea is, I mean, what you're seeing in that row is an entire DNA sequence. It should be zeros and ones. Those zeros and ones are generated according to independent coin flips of different probabilities, obviously. But that word independent is the moment where kind of you're paying careful attention. You should say, well, that may not match before. Okay. Pause there for a second, just because that needs to be internalized. And I need some more water. What I'll say right now is, believe it or not, that's actually not far off from reality. It's not the exact reality. But the absolute, if you speak to kind of the bioinformaticians, they would get you pretty close to that model, in fact. They're always, in fact, aiming for that exact same model. And what they would tell you is, okay, for a given cancer type, maybe no, it is not an entirely independent model, but it is in fact, at best, a mixture of, let's say, 3 of those independent models. Now, a mixture of 3 of those independent models is not the same as an independent model. It's not. I'm telling you that right now. But it is also not some completely arbitrary nonsense. So I just want to claim that what I'm about to talk about is not completely useless, right? But that there are also interesting open problems, which is kind of the middle spot that we aim for. Also realize I'm like 1 slide behind on animations. You all should have been seeing that last bullet. I apologize. Yeah. This is, by the way, what I'm describing. This is not the optimization problem yet, right? This is a model, a probabilistic model for the very first time, right, of kind of DNA mutation. I mean, there's a separate question of what optimization problem that we're solving. What I'll end with, I have just a couple of minutes. I'll tell you kind of the actual optimization problem you'd solve with respect to this model, which, I mean, again, you're given this mutation model. What is the optimization problem that you're solving? I'll tell you what we actually did. And then we'll kind of leave off on where we as the royal community might go. Okay, here's the problem where so you are given this capital P. Keep that in mind, right? This table is given. That's not the challenge. Here's the challenge. Somebody comes in. They have an unknown cancer type. Now, this sounds like a strict assumption. It's not. Their cancer type is drawn randomly according to some unknown prior. That is not crazy, right? I happen to know that 1% of people have lung cancer, 0.5% of people have pancreatic cancer. So, I mean, I assume that this random person that's walked in is drawn according to that same distribution. Okay, that distribution is pi. Okay. At this point, there are a number of actual optimization problems we could solve. If you kind of if you check out the paper that's public and kind of attached to this talk, you'll see 2 different ones. Here's one that I think is the most interesting. Here's the partially adaptive problem. The basic idea is this: you're going to construct a test. It's not like in the first half where you just select a bunch of addresses and sequence those, right? There has to be something quote unquote adaptive here. And the idea is this: you're going to select a sequence, an ordering of DNA addresses. I'll use the word sequence, and I feel a little bad. I'm overloading the word sequence here. Previously, I said sequence to mean DNA sequencing and what the biologists do. Now I mean sequence like mathematically, like an ordering of items. You're going to select a sequence of DNA addresses. And the key here is that sequence will always remain the same. But when somebody comes in for a test, you can stop whenever you want. So let me say it in pure English, right? I know when somebody comes in for their test for the very beginning, I'm going to start by looking at, this particular address of their DNA. address 1,000,000.5. There's a particular letter that I know is particularly informative. Okay. Based on that result, I can't change whichever letter I'm looking at next, whichever address I'm looking at next. I have to look at the same address next. Okay, and the third address, fourth, fifth, so on. But I can choose whenever I stop. I understand this is a subtle, this is not what you expected when you heard adaptive. When you heard adaptive, you thought that meant I would look at one address to begin with, I would look at the result, and that would dictate what I'll measure next. There's a practical reason not to consider those types of algorithms. And I'm scared to say that because we also do consider those types of algorithms. But there's like from a modeling perspective, that's a little off. And the idea is this: the lab that's doing this sequencing pays a massive fixed cost for separate biological reasons, a massive fixed cost for looking at any particular address. All right, put it another way, the lab, if it decides to look at a particular address for one person, might as well look at it for everybody. Okay, and so this, I mean, we're kind of at the opposite extreme here. The idea is this lab has kind of a workflow where it'll consider different addresses, and all it's really deciding is when to stop and say, hey, this person has a particular type of cancer. Okay. If, by the way, you don't feel particularly, if you don't believe this is particularly, feasible or not feasible, it's obviously feasible. If you don't believe that it's kind of, actually, if you don't believe it's believable, we got other results for the exact opposite extreme, which is that, you know, the lab can do whatever it wants, right? And in fact, by the way, the middle ground between those two is very much kind of another future direction. Okay. Well, I like this partially adaptive. It kind of illustrates the, you know, the flavor of what we could do. Okay, I don't have a full problem yet, right? This is just defining kind of the decision space. The decision space here is what sequence of DNA addresses you're going to look at, right? And the game is this: you have one constraint. You've got to identify the cancer type correctly with probability, something that you're told, like 99%. Actually, I said more like 75%. You've got to achieve 75% accuracy, no matter what the cancer type. And the goal is to minimize cost. That's it. By the way, I could have flipped those two. I could have said you've got to respect a certain cost and achieve a certain accuracy. The two are the same. The only theory I'll give, I won't have time to talk about the algorithm, but that's okay. I mean, that's a recipe, whatever. Here's what we're like here's where the math comes in, right? Like here's why I think we are useful as optimizers, right? It's because we can show results like the following. I mean, this is like this is a theoretical guarantee. There's a theorem behind this, right? Remember, capital A is the number of DNA addresses. That's 3 billion. That's huge. I just mean that's a huge number. Capital T is the number of cancer types. That's small. That's like 50. That's not growing, right? And finally, keep one letter in mind. I need a new one. Capital L is the maximum length or the number of addresses of a test. I'm going to use 10,000 as kind of the upper bound because that, you know, that's what we're constrained to be. Here's what a theoretical result looks like, right? You could try brute force. Brute force means just try every single sequence. That's all we're deciding, a sequence of DNA addresses. Now I'm looking at two numbers at once, right? On the far right, that's probably the most important, cost guarantee. I'm using this as a moment to define the term opt. Brute force means try every solution, and it should be no surprise that it will achieve the optimal cost. We'll call that thing opt. I'm fine with that. It's the runtime that I don't like, right? In terms of runtime, that'll take you A to the power L. A is 3 billion. L is, I don't care what it is. It's not 1, right? This is a huge number. So I put that in red because I don't like it. At best, we do have some heuristic that'll work here. I like this heuristic. I'll stare at runtime. Okay, A T squared. T squared, whatever, it's a small number. I like that this is linear in A, which was 3 billion, by the way, right? What I don't like, in red again, is that there's no guarantee. And I should say there's good reason to believe you would not be able to prove a guarantee on this same algorithm. Okay, where we might come in, right, and folks that kind of like, I want to be clear, like Nagshavara and Javidi are also optimizers. They're studying like a slightly different problem. So, but like where we can go, right, in 2022, as optimizers is results like these, right? What we did with Gan, Jia, Tyre, and Lee, right, is the following result. We have an algorithm. Its runtime is ATL. Again, A is the only big number here. That's what matters. It's an algorithm you can and we did run. Okay, and it's cost guarantee. No, it's not opt. That would be awesome, right? We pay an extra cost of a factor of log t. And by the way, there's mathematical reasons to believe this is the best you could ever do. I have some algorithmic ideas here. I'll post the slides. Probably what I should do, because this video is recorded. Y'all saw those slides just now. You can actually pause the video. Let me just end this with kind of, let me go back to this. This was the bad news picture. This is the good news, bad news, kind of whatever. I said, look, this was the optimal non-adaptive panels, right? This was the, just apply optimization to the previous problem. You went from the gray curves to the red curves. This was in some ways bad news, okay? Let me show you kind of the net result. Now you go from red to yellow. The yellow is a little strange. They're not optimal. The adaptive problem is a really hard problem, and I don't know what the optimal solution is. But if you just apply a reasonable algorithm, you can get something there, right? And you'll see a big jump. So obviously, I mean, I've cherry picked a little, but like there's reason to believe that adaptivity plus some knowledge in terms of algorithms will get you pretty close. So just summarize, right? I mean, like more broadly, and you know, like I'm happy to talk to anyone offline about this. Believe it or not, we're extremely close to the day where you have a cancer blood test done with your yearly blood work, right? With kind of the same test that measures your blood sugar, right? It took 30 years ago, somebody discovered this notion of cell-free DNA. It took 15 years ago, a whole team to invent next generation sequencing. And don't believe that I'm kind of exaggerating here. I think optimization might be that last step. I mean, I have a lot of versions of those problems that we would need to solve, but this is kind of, I view it as kind of a free way to improve on that cost accuracy curve. All right, I've gone a little bit over, I apologize, but that's the end of my talk. Thank you all for listening.
All right, thank you, Andrew, for this amazing talk. All right, so everyone from the audience, feel free to type your questions in the chat box. We can discuss that. We have a few more minutes. Yeah, maybe I just have a quick question first. I'm curious. You highlight the red, the pink area, the what do you call that? A region, the competing region. Sure. The reason you choose above 75% is that because for the gray line at the end of the gray line is still below 75.
No, great. So the back end, wow, a long time ago, feels like forever ago. An hour ago, I told you there's a test that actually gets to 75%. That's the gray curve. That gray curve, if you I'll give you an exact number. If you plot this curve horizontally 5 times further, the gray curve will eventually achieve 75%. That's the test that you can have done right now. Okay. That is a commercial test. Right. And so basically you have to imagine this plot, just like much longer. The gray will eventually reach 75%. Now, I don't know if 75%, by the way, is like the right benchmark. I actually think it's not high enough. Okay. In fact, I would like that. There's a reason your doctor will not recommend that you have this test right now. And it's because 75 is way too low. But in any case, we took that as kind of the benchmark. So there's nothing scientific about 75, by the way, being the right mark. But it's like that was a nice benchmark that I kind of didn't think of.
Okay, cool. So actually, you talked about the adaptive algorithm. You said it's not that kind of adaptive. It's not like depending on the previous address determine the next address. But I think the adaptive still makes sense to me because the stopping rule is adaptive, right? In some sense.
Precisely. Yeah. So I mean, this isn't like going back to partially adapt, like that notion. Like I mean, it's not like the moment you stare at that, it almost seems non-adaptive. No. I mean, it's very much adaptive, right? And the stopping rule is kind of non-trivial here. But in fact, like I'll take this as a moment to kind of talk about we considered both extremes. I'll consider this as one extreme, which is like the lowest level of adaptivity. The other being basically a decision tree.
Yeah.
Right. What I've seen before should dictate what even address that I sequence. I've talked about future directions. Like, I don't claim this is the end of the work. If it was, then we'd be done, right? No, like one direction is really like real life lives in the middle. And there's a combination of modeling and optimization to be done there, right? So there's like that middle ground contains problems that, well, both A, like modelers need to think about selecting between, and B, like honestly, problems that have not been solved. Right, because that really is the reality. Reality does not match what I call partial adaptivity here, or what kind of most of us would think of as adaptivity, the full version, right? The reality is really somewhere in between. It's very complicated, unfortunately. But I mean, that's kind of where. But they're optimization problems, right? Which is I think the fun part. They're not biological problems.
Okay. Okay, we've got one comment from the chat. Let's see. Okay. Thank you very much.
Oh, I want to grab if you give me let me throw the answer to this one. Okay. Let me repeat the question, and then maybe we'll call this the last one. The question is these tests, like Galeri, estimate their sensitivity and specificity on retrospective samples. When applied prospectively, their accuracy is expected to be lower. Can we expect that our contribution, of R is larger or whatever? That's okay. Now this is my favorite, this is my absolute favorite question. Okay, let's just look at this picture for a second. It's actually the reverse of what you think. This picture, I mean, really is from Cohen et al. Right? Cohen et al. Did this retrospectively. When they ran this in practice, prospectively, their accuracy went up. And this has been seen time and time again. Believe it or not, our offline data, right, is actually harder to achieve certain accuracy. Like this is like telling a machine learner that oh, you received, like you got a certain training accuracy, your test accuracy is actually going to go up. That is what we consistently see. I don't have a good, I'm not prescribing anything from that, right? But like, that's a really cool observation. And that's what these folks have seen. The actual numbers that Galeri advertises are from real tests, by the way. So, I mean, those guys are, like legally above board, I promise. But this is an awesome question. I love that question. Okay. The organizing team, I'll let you end. Yeah, thanks.
Okay. All right. So I think also time's up. And thanks everyone for joining this excellent, amazing talk. And wish everyone have a great weekend. And just announcement for future seminar series. We already have a few great speakers lined up for the rest of this year until September. So the same time, fourth Friday, 1 p.m. to 2 p.m. Eastern time, and that's our online seminar series. And I think that's it. And let's thank our speaker again. And looking forward to see you guys in the next time. Thank you, guys.
Everybody.
Thank you, Andrew.